All right. Hey, guys. All right. So we've made it through a few lectures so far on bounded operators and unbounded operators in a few cases. And so I want to continue this work that we've been doing in operator theory, and I want to make a move into talking about, second, into the spectrum. So one of our goals in this sequence I'm working on, is to go into what's called spectral theory, which basically characterizes completely the spectrum of operators with various properties. So the spectrum theorem for compact operators, compact self-adjoint operators, ends up being just a diagonal. The spectrum ends up being a point spectrum, so only eigenvalues, and they decay to zero. And then we can see what it happens for more general and normal and self-adjoint bounded operators, which will take additional work. But today, before we can get into any of that stuff, we need to talk about, the definition of spectrum, what the heck it is, and and start getting into it. The ultimate goal is to work on some more look at the interactions between operators and say data science down the line when we talk about, say, dynamic mode decomposition, singular value decomposition, and other things like that. We can also take a look at the interactions with quantum mechanics and the Schrodinger operator, though I'm going to have to do some reviewing of my quantum mechanics. It's been a few years. And then also we would like to talk about some other things, like the Sturm-Liouville problems, which are a classic problem from the 19th century, which involves spectra and also differential equations and boundary value problems. So I have about an hour today to throw at this, so we'll see where we can get. Basically, a typical lecture length, and anything I want to mention? Still working on that video. It's going to come out on divergent integrals. That's taking a little bit longer than I expected. Just trying to find the time to do all the MATLAB figures and things like that. That's really the biggest bottleneck, is all the figures and equation writing around all these videos. It takes so long, and you can't really outsource it because, I mean, it's not like your typical editor is going to know one equation from another one. So, anyway, so let's take a look at my. Okay, so that was awkward. Let me adjust this so it's not so loud. There we go. Okay, so can you guys hear me now? I guess I'll have to wait a second. There's a delay. Okay, so seeing this thing go off, hopefully that means that I have a sound now. That was weird. Oh well. I was in such a rush to get everything set up that I guess I forgot to check the microphone. Okay, thank you guys. All right, so let's go ahead and start over again. I welcome, and so today we're going to be talking about a spectrum of operators and all that good stuff. And so we're going to define the spectrum. We're going to define the resolvent. We're going to show that the resolvent is actually an open set, which then will lead us directly into the compactness of the spectrum, which is nice. And so then the idea is that we're going to take a look at the point spectrum, the continuous spectrum, and the residual, and find what all those are. And so this is all very typical stuff out of operator theory, and our general goal is to get this out, get to the spectral theorem for both the say compact operators and then also for bounded operators and self-adjoint normal operators, things like that. And so we're going to go through this. A lot of this is going to be definitions and really straightforward proofs of small theorems. Then I want to end this lecture, whether or not that ends today or next time we meet, with some examples over the Hardy space where you can get a complete characterization of the spectrum of the multiplication operator by Z, or the shift operator, and its adjoint, which is called the backward shift. And so this is sort of a nice little introduction, and so it should be mostly self-contained. And like I said, we'll try to get it done today. If not today, we'll get it done. Actually, not next week. We won't stream it next week, but the week after that we will. Next week's spring break, so could be occupied. All right, and so thank you everybody for just sitting in here while I just blabbered at a screen, not realizing my microphone wasn't working. And so I think there was Okoyoso, you had a question about are matrices bounded operators, and the answer is yes. And so essentially, if you're working with a matrix, then say finite matrix. You could have an infinite matrix, but we're talking about finite matrices. For finite matrices, that's a finite dimensional. That is a linear transformation on a finite dimensional vector space. And linear transformations over finite dimensional vector spaces are always continuous, and boundedness is equivalent to continuous. And so, therefore, that means that all of the things you would experience in, say, linear algebra, all of those are bounded operators. So it's not terribly exciting talking about that from the more operator theory perspective, but a lot of things we're going to be saying do actually apply to matrices, and we will get to that eventually. And the most simple example of a spectrum that you've probably seen is actually related to matrices, and that is eigenvalues of a matrix are actually in spectrum. And so matrices only have point spectrum, and they only have eigenvalues. And so they don't have any of the continuous eigenvalues, and they don't have any of the residual eigenvalue, or continuous spectrum, or they don't have residual spectrum. They only have eigenvalues. And so another way to think of matrices are they are finite rank operators. So you could have a sort of a subset of a much larger space that you're just really focused on, even if you're talking about a much broader operator. So for instance, you could take the Fourier transform, which is a bounded operator over L2, and you can take a look at these sort of invariant subspaces for the Fourier transform, which are expressed by the Hermite functions. And so if you have a finite span of Hermite functions, then the Fourier transform acts on that space as a linear transformation from that finite span to that finite span. Well, finite span being like, all of them from, say, Hermite functions from 0 to like n. And then in that case, you can just treat the Fourier transform just like a matrix, and then it produces eigenvalues. So I guess that is our example of a bounded operator with just pure point spectrum. Okay. All right. So I blabber when I lecture. I guess I fill the space a lot, and that's why whenever you get a professor started talking, they just never shut up. They just get trained to always to fill the space. But okay, let's start with the definition of the spectrum. So let's cut this in half, and here. So definition. All right. So for a bounded operator, A, the spectrum of A, denoted as small sigma, subset of the complex numbers, is the collection of points lambda and c such that we have A minus lambda I, where I is the identity matrix, is not invertible. All right. And the resolvent of A is defined to be, say, row of A, all those complex numbers where it is invertible. So it's a complement of the spectrum. All right, so like I said, eigenvalues are a very straightforward way of talking about this. So, example, if M is a matrix and lambda is in C is an eigenvalue, of M, then with eigenvalue, with eigenvector, V, then we have M minus lambda I acting on V is going to be the same as lambda V minus lambda V is equal to 0. And so the null space there, so which implies that the null space of M is not just the 0 vector. And so the rank nullity theorem tells us that the rank of M is less than the dimension of whatever the vector space you're working over is. And so that implies, or sorry, not M, but rank of M minus lambda I, which implies that M minus lambda I is not surjective, which implies it is not invertible. Okay, I think I just really like using rank nullity theorem. I suppose that I could have just said it's obviously not one-to-one because the M minus lambda I also sends 0 to 0. So, but then therefore lambda is inside of C. Okay, but it's kind of interesting though that the rank nullity theorem basically makes this idea of not filling out the range, making the range not fill out the codomain fairly, the same thing. And so here we could have just stopped here and said, all right, so it sends V to 0, but also sends 0 to 0, so it's not one-to-one, therefore done. It's not invertible. But another thing though is that this simultaneously told us that the rank is deficient. And so the range is deficient in such a way. And so when we talk about these other kinds of spectra in the infinite dimensional case, we don't have the rank nullity theorem, and so they end up getting different. And so the point spectrum doesn't always mean that you don't fill out the range. All right, okay, so thank you for the acknowledgement. I do appreciate that you like the blabber. So do I have a routine or schedule when I stream? I try to stream about once a week on Wednesdays. I've been hesitant to make a declaration like I'm going to be out here every Wednesday, just because other sort of random things come up. Sometimes my kids are sick and I just can't stream, or meetings fall on top of here, and meetings for work sort of take precedence over sort of my fun hangout time on YouTube, and I does that have anything to do? And so I don't know. I don't have a fixed stream, but I'm trying to be here around 11 o'clock on Wednesdays, 11:30 or thereabouts, and that's basically the earliest I can really get on to stream. And so I have a small window between on Wednesdays when I have to drop the kids off to school and pick them up, and so this is sort of like the sweet spot where this sort of thing can happen. And it also encourages me to help move forward on the book that I've been writing, and so you guys can sort of hold me accountable. Okay, so now back to a math question. Does this have anything to do with the spectrum of a ring and a set of prime ideals? To be honest, I'm really rusty with my my algebra, and so I don't know. Specifically, in the set of in ring theory, it probably does. I'd be very surprised if there was no connection there. The usually, as far as I get for in algebras, like in Banach algebras, and that's mostly where I hang out. So I apologize. I don't have a more solid answer for you. I'll look it up and I'll let you know next time. It probably has a connection, and I just need to sit down and do it. It's just been a minute. Once I got out of my PhD qualifiers for algebra, I never really looked back, and so I know the basics, but it's been a while. So, okay, let's see. Okay, so we have definition. That's great. What was next on the list? All right, we want the openness of the resolvent. So in order to get the openness of the resolvent, we have to prove another thing about bounded invertible operators, and so we're going to use the von Neumann series. I don't think it's the Neumann series. I think it's the von Neumann series. Neumann was a mathematician in the 19th century, von Neumann in the 20th century, but like they're separated by von, and which makes it very confusing to try to keep it track in your head. So, so what we're gonna have is let's call this a theorem, proposition if you want. This I think it was actually an exercise in Pedersen's analysis now, if I remember correctly. But basically, if A is an invertible operator on a Hilbert space, and B is also a bounded linear operator, is a bounded invertible operator, I should probably say, bounded invertible operator, and B is in LFH as well, such that we have that the norm of A minus B is less than or equal to 1 over the inverse, sorry, not that one, the reciprocal of the norm of the inverse of A. Then B is invertible. Right, and so this is going to help us get a nice result for the spectrum, where basically we're going to get the resolvent, which is a collection of all those guys where like A minus lambda I are invertible, and so you can see how this can sort of come into play. So in order to get this guy, let's have one quick lemma. If the norm of A is less than 1, then I minus A is invertible. Okay, so let's go and prove that first. All right, so proof. All right, so here we're going to need one thing from Banach spaces. I'm just going to state it. So from Banach spaces, absolutely convergent series are convergent. Right, so that's a really fundamental fact. It's sort of a day one Banach spaces sort of thing. And so what we're going to have then, what we're going to do then is we're just going to basically take a look at this. And so the series sum of an, n equals 0 to infinity, is convergent since the sum of an is less than or equal to the sum of the norm of A to the n, which is equal to 1 over 1 minus the norm of A. And so, since that series is convergent, what we can do then is we can go ahead and work like this. So we can take a look at I minus a, and take a look at I plus a a squared, etc. So we can be assured that this is a well-defined operation. Then all we need to do is distribute to both sides, and so we have just your typical definition here. So we're going to have I times the series, and then we're going to have minus a times the series. So it's going to be shifted over by 1. And so if you take a look at the difference between these two guys, all that's going to be left is we've canceled everything but the I, and so then that leaves I. And so by definition, this converges. And by definition, this is invertible. And so this says that I minus a inverse is equal to the sum of a to the n equals 0 to infinity, which is a nice result. So it's a geometric series. It works here in the space of operators, which is nice. Let's see. All right. So, all right, so that's good. All right, so now we have this first little result of invertible operators. That basically I minus a is invertible if the norm of a is less than 1, which corresponds to what we know about geometric series, where basically that series definition works out great as long as little a is less than 1 in magnitude generally. So we can go ahead and use that here. Okay, so what's next? If we take a look at this theorem that we want to prove, so we'll say proof of theorem. So what we're going to do is we're going to go ahead and look at the board to see what I proved earlier. Yeah. Okay. So what we have then is, remember, we were saying that the norm of a minus b is less than or equal to 1 over the norm of a inverse. And so what I'm going to look at then is I'm going to take a look at I minus, say, a inverse of a minus b. I think that's right. Yep. And so if we consider this, so I guess I consider, then this is invertible. Since we have the norm of a inverse a minus b, smooths over a little bit, is less than or equal to the norm of a inverse a minus b, which is less than or equal to 1 just by our hypothesis. And so that's nice. And we have that I minus a inverse a minus b is equal to a inverse b. And since and then this can show us that b has to be invertible as well. Just hold on. I should have finished this proof earlier. I just worked out this far. Let's see. So in order to get that, we're going to have a inverse b. And so a inverse b is invertible. We'll say that. All right, so now let's move to the next page, and we'll continue the proof. So now our claim is if A is invertible, and A inverse B is invertible, then B is invertible. Okay, so let's go ahead and take a look. So we have A inverse B inverse hitting on A inverse B is equal to I. And let's see. Do I want to do this the other way around? Maybe. Oh yeah, no, that's trivial. Okay, so yeah, then that gives us A inverse B A inverse B inverse times A inverse times B. That's the worst B I've ever written in my life. There we go. Is equal to I, and so B inverse is equal to A inverse B inverse A inverse blah. There we go. And so then done. Okay, so that's a nice little result. Okay, so then that's what we have. So we have proved that if A is an invertible operator on a Hilbert space and B, oops, is erased. That's not good. And B is close to A, and in particular it has to be closer than this, then B is also invertible. What that tells us then is that the collection of invertible operators are actually open in the topology that is induced by the operator norm, which is pretty nice. And so, corollary. The collection of invertible bounded operators is open in the topology induced by the operator norm. In shorthand, we say the norm topology. Okay, so that's good so far. All right, but we don't want this only for operators. We also want to see this apply for the spectrum. So our claim, so I guess it'd say theorem or proposition, is that the resolvent of a bounded operator is a non-empty open set. Okay, so proof. All right, so we need to first show that it's non-empty. And so what we're going to do is going to let, say, lambda B and C such that the norm of the magnitude of lambda is bigger than the norm of A. Oops. I don't know, GoodNotes added these like AI tools, which are really annoying. They just want to take over everything that you're doing. They want to take every math equation you write and they want to turn it into LaTeX. They want to jump in and give comments everywhere. It's getting very, very frustrating. Anyway, so let's go ahead and we're going to let lambda be a complex number such that the magnitude of lambda is bigger than the norm of A. All right, so that implies that A times 1 over lambda, which is a perfectly reasonable operator, has norm less than 1, which then implies that I minus 1 over lambda times A is invertible. Okay, and if you're paying attention, I should also probably say we're going to just exclude 0. Okay, but I guess that was kind of true because we're saying that the magnitude of lambda is bigger than norm of A, so even if norm of A was 0, lambda would still be bigger than that. Anyway, but just to be explicit, we're not including 0. And let's see. So, and then this implies that lambda minus, say, A minus lambda I is invertible. Which itself implies that lambda is inside of the complement of the spectrum, rho of A. Let's see. Does this only give... so the way we defined... let's see. Left inverses. Yeah, you're right. So I didn't get the other side of B. I was being too quick. All right, so the question is, doesn't this only give a left inverse of B? And so you'd have to just work out the same sort of deal with the other side of B. So remember, we did define inverses to be both left and right inverses. So let's do a little bit of scratch to get that other side. Let's see. Okay. So some scratch. So if we have A inverse B, and so we said that this was invertible, so this would work too. And let's see. Yeah, maybe this side only works out. This would still only give you the left inverse. But if let's take a look at that proof again. I think there was an extra step in there that maybe we can still exploit. Yeah, so that whole thing with the Neumann series, you basically you can do the whole thing again, where in the proof we gave, it was like this. And then we got that this is invertible. And that is equal to A inverse B. But we can also do this one. Right? And then, sorry for my chicken scratch. And then this is equal to B A inverse. And that is invertible. Under the same hypothesis, which would then give you that B is left and right. Invertible. You're right, I was too hasty. But yeah, thanks for catching that. So yeah, so that's how you would resolve that one. So same argument, otherwise, it's just where you put that A inverse in that series. All right, thank you, Koyoso. Okay. All right. So back to this guy. The resolvent of is non-empty. So we got non-emptiness. That's check. So non-empty. And now we want to get that's open. And so so I guess what was that? Yeah. So continuing. Okay. My intention is to upload a lot of these up to my Discord for all these lecture notes and stuff like that. So, or share them through my newsletter, which is something that is still being put together. But yeah. All right. So continuing the theorem. All right. So we have non-emptiness. Now we want to show that it's open. So we're going to let lambda be in our resolvent set. And then consider, let's say, lambda and mu in the resolvent set of A. Then we're going to consider A minus lambda I minus A minus mu I in norm. But you'll notice that the A's annihilate, and so that leaves us with mu minus lambda times I. And, well, then that is equal to the absolute value of mu minus lambda. So if we select, so if mu minus lambda in absolute value is less than, say, 1 over the norm of A minus lambda I inverse in norm, here, actually, let's say I need to make it just lambda. So mu is arbitrary in the complex plane. So then if this happens, then that tells us that A minus mu I is invertible, which implies that mu is inside of rho of A, or the resolvent. And so then that is the definition of openness. So that 1 over A minus lambda I inverse is norm, is our epsilon and for our balls. So, good. So we have a non-empty open resolvent. So what I'd like to show then is that the spectrum itself is compact. And to do that, so theorem, something that's used quite a lot for a bounded operator A, sigma A is compact. All right, so proof. So we already have that sigma A is bounded by the norm of A, because if you're bigger than the norm of A, then you are in the resolvent. We showed that last time. And so I already proved. And so all we need to do, and then I guess we should just say, and since sigma of A is equal to the complement of the resolvent set, that tells us that sigma A is closed. And so sigma A is a compact subset of C by Heine-Borel theorem. So ordinary analysis. So not too bad. So I would say significantly, the what we have not shown is that the spectrum is actually non-empty. That turns out to take a lot more time to work out. Well, not really a lot more time, but I want to talk about some of the complex analysis that goes into it. And so getting a non-empty spectrum is going to require us to use Liouville's theorem that basically says that any bounded entire function is constant. And so in order to do that, I want to just talk about a little bit of the complex analysis that goes into that, and then we can talk about all that good stuff. So, but just for the sake of it, I'll say it now. For any bounded operator, the spectrum is actually non-empty, and we'll prove that later. Okay, so the goal is to see if we can find some examples. And so let's take a look here. Let me see if for what we had here. Okay, so thus far, I have this. We've done that. All right, so this one we need to do, just characterization of the spectrum. So in these examples, I want to go through all these various kinds of spectra that you can run into. I found in the class I teach that the multiplication operator, the shift operator on the Hardy space, turns out to be a really great way of demonstrating that. And so I only have about like 5-10 minutes left here, but I think I can at least get through the characterization of the spectrum, and maybe we can prove one or two things, and then we'll wrap it up next time with multiplication. But let's try to get that done. Okay, so so let's get a new page. Shoop. All right, so types of spectra. All right, so we saw one example of what's called a point spectra. So this is lambda in sigma A, such that A minus lambda I has non-trivial null space. Right, and so in particular, there exists a V inside of H such that A minus lambda I acting on V is equal to 0, which implies then that A V is equal to lambda V. So eigenvalues and eigenvectors. Okay, so that's the 101 version of the spectrum that you see most people talk about, and that's what you learn in your ordinary linear algebra course. Okay, so but there's other ways to be not invertible, and so so you could have it so that you are still a 1-to-1 map. So, but it might be that your range is deficient in some way, and so so that means that you just don't hit all of the range. But there's two ways to do that. Well, there's a lot of ways to do that, but two that we care about. And so one, and this is the continuous spectrum. And so this is the lambda in C, A, such that A minus lambda I has dense range in H. In other words, if we take a look at the range of A minus lambda I, and we take its closure and the Hilbert space norm, then that's equal to H. So we can't, our range isn't everything in H, but we can approximate anything in H with a member of our range. One example, at least a quick example I can give you, is basically if your range consists of polynomials, it has all the polynomials in it, then that would work. I guess an unbounded version example I can give you is just differentiation, right? So the derivative of polynomials are polynomials, and so the span of the range of the differentiation operator is going to be all of H. And so that's what you get. And then we have one other kind of operator, and that is called, or one kind of spectra, and this is the residual spectrum. And so this is lambda and sigma A, such that the range is not dense in H. Okay, and so that means that if you take a look at, that means that the perp space, so just say the range of A minus lambda I perp is not trivial, because if that was true, then that would mean that the range of A minus lambda I was actually all of H. So putting that together, I think I actually proved that in my last video on YouTube, actually. So if you just check out the last proper video, I have a proof of that. But yeah, so at this point, then that gives us three different ones. We should also note that, so this is a claim. You can prove this on your own. But basically, the range of A minus lambda I perp is the same as the null space of A minus, right? Let me say not just A, just any operator. Let's put B. Null space of B star. And so that's a really nice connection here. So it's one way to check this, this condition, which is what we will use. I really it just comes from just taking a look at the inner product. It's fairly straightforward. Okay, so let's see. What else we got? So there's a different types of spectra. So let's talk about a couple of examples with the multiplication operator. This honestly shouldn't take too long. So remember, we're going to be working over the Hardy space. So H2 of D, and so this is functions f of z, such that they are written as a series an z to the n, such that the sum of an squared is less than infinity. It's the Hardy space, and the inner product here between f and g is equal to the sum of an bn bar, where bn is the coefficients from g. There. Okay, so let's see. So now we're going to be talking about the multiplication operator, m of z. M of z basically multiplies f by z, and so is basically shifting things over. So it gives you a n z to the n plus 1, n equals 0 to infinity. And another way to write it is n equals 1 to infinity of a n minus 1 z to the n. And so if we think of this in terms of the sequence, we have a naught, a1, etc., is being mapped to 0, a naught, a1, etc. Okay, and so that's the operator we're going to be looking at. Since it's only just shifting these coefficients and the norm of the operator is really just coming from this, then we have the norm of mz is equal to just 1. Okay, and as far as left invertible and right invertible, this is a great example showing that this operator is only invertible on one side. So you can hit it with the backward shift on the other side, which is its adjoint. I should also mention that. We proved this last time. Mz is equal to f of z minus f at 0 divided by z, or it sends a naught, a1, etc. to a1, a2, etc. And so here we have that mz star times mz is the identity, but the other way around annihilates a0. So, okay, so what we're going to show is first that, so claim 1, mz has no point spectra. And so we can take a look at is this. We're going to let lambda and norm be less than 1, or less than or equal to maybe. And we'll see if I need to make an adjustment later. I didn't actually practice this ahead of time. So if it had a point spectra, so assume by way of contradiction that there exists some f sub lambda in H such that mz minus lambda I of f of lambda is equal to 0. Well then, what does that say? Well, if we take a look at mz minus lambda I, each of these terms are going to be written like this. So it's going to be 0 minus lambda a0. It's going to be a0 minus lambda a1. And it's going to give us a1 minus lambda a2, etc. So it gives us this recursion on our coefficients. And so this tells us that for and all of this should be equal to 0, I should say. So for so the first term tells us that 0 minus lambda a naught is equal to 0. And so I guess let's assume initially we're going to assume that lambda is not 0. So if lambda is not 0, then basically this implies that a naught is 0, and which then implies a naught minus lambda a1 is 0, implies that a1 is 0, etc. And so we have an is equal to 0 for all n, and which implies that f lambda is 0, and m minus mz minus lambda I has a trivial null space. Okay. Does that line up with my definition? Suddenly yeah, so non-trivial null space has trivial null space. Okay, good. All right, so we have to worry about lambda being 0 now. Let's see. So if lambda was 0, if lambda is equal to 0, then if mzf say sub 0 is equal to 0, this implies that the norm of mf is equal to the norm of f, because the norms are equal, and so then this is just going to be f is 0, and so therefore mz has a trivial null space. Okay, so that's done. Okay, so now let's take a look. Now we know that m of z actually has a non-empty spectrum, because I told you. But let's see what we can find as far as other kinds of spectra. So there's one thing we should probably mention, is that if lambda is inside, so I'm just going to put this as a claim. If lambda is inside the spectrum of A, then lambda bar is inside the spectrum of A star. All right, that's easy enough to prove. You can go ahead and do that. And so what we're going to see, though, is that we can get something a lot stronger out of the backward shift than we can out of the forward shift. And so then we'll see that we're going to get a whole spectrum, an infinite number of spectral points for A from for MZ from MC star. So let's go and take a look. So so now our next claim is lambda with norm less than 1 is an eigenvalue for MZ star. Okay, and that's not actually too bad to prove. And so what we're going to do is we're going to take a look, we're going to consider I'm going to call this f lambda is the sum of lambda to the n, z to the n, lambda bar n, z to the n, and says is n equals 0 to infinity, or is 1 over 1 minus lambda bar z. If you have any experience with reproducing kernel Hilbert spaces, or the Hardy space in particular, you'll recognize this as the Szego kernel, which is a reproducing kernel for the space. We talked about this a few weeks ago. So we can note that the sequence that we have here is going to be lambda bar, no, 0. So it's going to be 1 lambda bar. I'm just going to take off the bar. The bar is just something I compulsively put because we're talking about lambda, not lambda bar. So so this is the reproducer kernel for lambda bar rather than just lambda. Lambda squared, lambda cubed, etc. And now this is mapped by mz star to lambda, lambda squared, etc., which is equal to lambda times 1 lambda, lambda squared, etc. And so just by using this sort of sequence analogy, we see that we have now kicked out an eigenvector and an eigenvalue. And so that works out really nicely. So, okay. So now that we have that, we now have an eigenvalue and an eigenvector. And so this implies the set D of all Z and C such that the norm of Z is less than 1 is a subset of MZ star. But since spectra is compact, we can take its closure and we still stay in there. And so that means that for absolute value of lambda less than or equal to 1, lambda is inside of sigma mz star, which is equal to lambda mz conjugate. And since this is symmetric under conjugation, that implies that d bar is actually equal to this. So that is basically, we know that MZ has a norm of 1, so we know that all the spectra have magnitude at least 1. And so if we take the closure of D, that is all of those lambdas, so it has to be the same. Okay, so let's see what we have. All right, so that means we're left with two kinds of eigenvectors that we still need to justify. So I'll try to stay on for a little bit longer and just finish this out. So we have an example of point spectra, and now we need a continuous spectrum and residual spectrum. Okay, so the residual spectrum is probably the easiest to get at. And so, so let's go ahead and do this. So, all right, so our claim here, if lambda is less than 1, then lambda is in the residual spectrum of A, or MZ, sorry, not just generic A, MZ. All right, so what do we do? Well, we're going to note that MZ minus lambda bar I MZ star, MZ star lambda I has non-trivial null space. But we have the null space of MZ star minus lambda bar I is the null space of MZ minus lambda I star, which is the same as the range of MZ minus lambda I perp. And so that's non-trivial, which implies that the range, and so non-trivial. So that implies that the range of MZ minus lambda I closure is not H. All right, so there you go. We have example of the residual spectra. And so that is, so the residual spectra of MZ is at least the set of all complex numbers of norm less than 1. Okay, so now what do we do about the ones that are equal to 1? Well, we can take a look at those directly. And so sorry, next claim. If normal lambda is equal to 1, then lambda is in the spectrum, the continuous spectrum. Of MZ. Okay. So let's see, how are we going to do this? So it'll probably just appeal to the same thing we just appealed to a second ago. Let's go ahead and take a look at, so we're going to consider the range of MZ minus lambda I, which is the same as the null space of MZ star minus lambda I. All right, of lambda bar I. And so if, let's say, f lambda is inside of the null space of MZ star minus lambda bar I, we have MZ star of f lambda is equal to lambda bar f lambda. And what does that mean? Well, that means that we're going to have A naught, A1, etc. for our f is being mapped to lambda A1, lambda A2, etc. Or, no, lambda, sorry, A naught, lambda A1, etc. And so, bar, etc. Okay. Is that right? No, I messed up one over here. Okay, sorry. Oh, that's stupid. All right, there we go. All right, left-hand side becomes A1, A2, A3, etc. And the right-hand side becomes lambda A naught bar, lambda bar A naught, lambda bar A1, etc. And so then that tells us then that lambda bar A naught is equal to A1, which then tells us that lambda bar A1 is equal to A2, etc. Okay. This should break somewhere. Just give me a second. Right. Okay, that's where it breaks. So that tells us then that AN is essentially equal to lambda bar to the n A naught. But with the norm this being 1, this implies that the sum of AN squared is infinity. And that's a contradiction because this was supposed to be inside of H. And so, therefore, the only way this could work is if A naught equals A1, etc. is equal to 0. All right, so then f lambda is the 0 function. And so, therefore, A naught equals A1 equals A2, etc. is equal to 0. And f lambda is a 0 function, which implies the null space of MZ star minus lambda bar I is trivial, which is equal to the range of mz minus lambda I perp, which implies then that the range of mz minus lambda I closure is equal to h. Whew. Okay, and so there you go. So that is a complete characterization of the of mz spectrum. So sigma of mz is equal to d closure, and so that is this. Inside we have residual, outside we have continuous, and for mz star, these inside guys are eigenvalues. So that is an example for an infinite dimensional operator and its complete characterization of a spectra. So you see here that we have a whole bunch of, we have an uncountable number of eigenvalues for mz star. We have no eigenvalues for mz. And then we have these two different kinds of spectra for mz all laid out here. Okay, so that's all I wanted to show for today. I actually got it done. It took about an hour and, what, 20, hour and 15 minutes, I guess. So that's not too bad. I think, yeah, that's good. Thank you guys for your help. Thank you for telling me my microphone was off. But I do have to end up going. I appreciate y'all for coming. Thank you so much for watching. And I really hope you guys have a great day.